Hello again, folks. For this second video on significant figures, we could talk about all of the rules, like leading zeros are never significant, but trailing zeros are sometimes significant, and things like that. And then we could go through some lame made-up examples. But there are plenty of resources all over the internet that can help you with that. What I'd like to talk about this time are three rules that I use, but I don't see them explicitly stated anywhere else. Rule 1. You're not trying to find the easiest way to get the answer, you're trying to find the hardest way to screw it up. For example, and this example is from real life, only slightly exaggerated for educational purposes. In an algebra class, we have two equations with two unknowns. Bob is paddling his canoe upstream and then downstream, with multiple segments each way and an unreasonably complicated mix of units. How fast can Bob paddle his canoe in still water? A student who shall remain nameless, it wasn't me by the way, though I've done things that were equally unsuccessful. This student got about half of the conversion factors upside down. There are 60 minutes in 1 second, 5,280 miles equals 1 foot, and so on. The student's final answer was that Bob can paddle his canoe at a little over 30,000 miles per hour. Now, you would think that there must be some part of your brain that would recognize whether Bob can paddle his canoe faster than Earth's escape velocity. But that part of your brain may or may not be active when you really need it, like when you're in test-taking panic mode. If you actually write things down on a piece of paper, you're giving that part of your brain one more chance to come to your rescue. Yes, when converting from centimeters to meters, you can just move the decimal point. But if you write things down, you are more likely to move the decimal point in the correct direction. Rule 2. In order to know how many significant figures you have in your measurement, sometimes you have to think about what you're doing. For example, you extract the good stuff from a sample, and then you run the extract through some instrument to tell you how much good stuff there is. Yesterday, the machine told you there was 5.40673954 milligrams per milliliter of good stuff. Today, the machine tells you 5.41045797 milligrams per milliliter. Does today's sample actually have a higher concentration of good stuff than the sample you extracted yesterday? The instrument is reporting a long string of numbers, but how many of those digits are significant? If your answer is, we always report to 4 significant figures, but I don't know why, you deserve a savage beating. When you were developing the extraction method, you did 5 extractions on 5 consecutive days, starting with the same homogeneous reference sample, and the instrument told you the following concentrations. The average concentration of good stuff for these 5 replicates is 3.966695908 milligrams per milliliter. These are all from the same homogeneous reference sample, so in theory, these should all have exactly the same concentration of good stuff. But there is some uncertainty in how homogeneous your reference sample really is, and there is some uncertainty in how reproducible your extraction method really is. By the way, these results actually look pretty decent if this were real life, with an RSD star of about 1.5%. Small digression. What the heck is RSD star? You can read those words if you want. You know what you have here, though? You have 2 significant figures, with the uncertainty in the first place after the decimal point. No matter how much your boss wants to think that today's sample has a higher concentration of good stuff than yesterday's sample, these are both 5.4 milligrams per milliliter to 2 significant figures. Sorry, boss. Another example. You're titrating a sample by adding a solution drop by drop from a burette. The burette is marked to the nearest tenth of a milliliter. Normally, you would use the rule that says you can estimate where the measurement is to 1 more decimal place than the markings on your measuring device. But can you really tell the difference between 48.15 milliliters and 48.17 milliliters? And I'm not talking about your eyesight, I'm talking about the size of the drop. What if your burette pretty consistently delivers 20 drops per milliliter? Then the average volume of each drop is 0.05 milliliters. If that's the size of each drop, there's no reason to try to distinguish between 48.15 milliliters and 48.17 milliliters. That difference is smaller than the actual size of the actual last drop of the titrant that you actually added to the sample. Maybe your best practice with this burette is to only report to the nearest 0.05 milliliters. In this neighborhood, you're trying to decide between 48.10 milliliters, 48.15 milliliters, and 48.20 milliliters. You can reasonably do that with reasonable eyesight, and you're including the uncertainty from the size of the drop. Rule 3. Your calculations are not being written on a clay tablet with a pointed stick. Use all the digits. Let's say you have a Pivnert problem. Your measurements are to 4 significant figures, and now you need to do some arithmetic with your measurements and the gas constant. The gas constant is one of those exact by definition numbers, at least it's exact since the 2019 revision of the SI units. But it's a fairly inconvenient exact number with lots of digits. Should you use 8,314 in your arithmetic? Should you use 8314.5? Should you do that what if thing where you try more and more digits of R and see what happens to the answer? Should you look up the rule that tells you how many digits of the gas constant to include for 4 significant figures? But your calculations are not being written on a clay tablet with a pointed stick. Your Excel spreadsheet will not mind if you use all the digits of R. And then you can round your answer to 4 significant figures, because the rule for multiplying and dividing significant figures is easy to remember. Summary. Rule 1. You're not trying to find the easiest way to get the answer, you're trying to find the hardest way to screw it up. Rule 2. In order to know how many significant figures you have in your measurement, sometimes you have to think about what you're doing. Rule 3. Your calculations are not being written on a clay tablet with a pointed stick. Use all the digits. Okay, that's enough for now. Thanks for listening. We'll talk more later.